Welcome back, everybody. So we're going to continue where we left off with power series, and we just kind of hit the jackpot of information. For whatever reason, okay, there we go. Which was that you can differentiate and integrate power series term by term, which is a big deal, even if you don't really realize it at the moment. Power series involve infinity. That is a very, very crazy concept that you can actually do it. And maybe this will help you realize it. I forgot to add this to the notes, so I wanted to add this as a bullet point. What can be characterized is basically you can bring differentiation on the inside of an infinite summation. We knew that was true with finite sums. And with integrals, that was true with finite sums of things. But now we know that we can do it for infinite sums, provided, of course, that you are on the radius of convergence. As long as you are within the radius of convergence, you can bring the derivative operation onto the inside of the summation and the integral sign onto the inside of the summation. That's what the big deal is. That isn't common. That's not a thing that we can just guarantee. It takes a lot of proving. In fact, there's a lot of things like this in mathematics that you will see. If you plan on taking Calc 2, Calc 3, we're in Calc 2. If you plan on taking Calc 3, you will talk about double integrals and triple integrals, which are very, very cool, very, very awesome. You might even go higher than that depending on your teacher. But regardless, there's a whole fact about it that says, and you don't need to write this down. I just want to gush about it a little bit. A double integral of a function f of x comma y dx dy. What you learn in that class is it in fact doesn't matter as long as your function is reasonable, which basically everything we deal with in mathematics is up until you get into upper division mathematics. You can rewrite this as f of x y dy dx. And the proof of that thing is incredibly difficult because what it has to do, if you remember the definition of an integral, a definite integral, is that it has to do with adding up infinitely many rectangles. And the way you do it in this case is it's a double summation. It's a summation from n equals 0 to infinity and m equals 0 to infinity of the stuff. And what this one of the theory like what this theorem is basically saying is that you can interchange these two summation symbols with infinitely many number of things. And that's a very hard theorem to prove. It's called Tonelli's theorem, and it's incredibly complicated. And so I just want you to kind of
Just for swapping those.
yes, just for swapping those two integration rules. Like we intuitively knew it at the time. We were we looked at several examples and was like, okay, so I can do it either way. But mathematicians don't want to know about specific examples. They want something that is very, very concrete that makes sure it works for everything. And proving that it works for any function that's reasonable is a very, very challenging proof. I had to use it in my thesis, actually. Use Tonelli's theorem. I had to bust that out. I haven't seen that in ages. So it is a big deal when you can mess around with summations and move them around as you see fit. So, anyways, back to the point, which we did talk about very, very quickly. Um, it's usually the case that for derivatives, when you take the derivative of a power series, the index lower bound increases by 1, whereas for integration, it usually just stays the same. That's not always guaranteed, and that's why when you write it out, you should just verify it, as we'll see in the next problem. But regardless, so you'll see that in this example here. So the function f of x, the power series from n equals 1 to infinity of x to the n, you're going to find the intervals of convergence for f of x, f prime of x, and the integral of f of x. So just first and foremost, let's find ROC for f. We're going to find the radius of convergence for f because the radius of convergence is consistent across the board, right? The first derivative, the integral, the second derivative, the second integral, the third derivative, and so on and so forth, they all have the same radius of convergence. So it makes sense to first find that, because that is what's required first before finding the intervals of convergence. Because remember, they all share the same radius, but they might not share the same interval. So how do you think we should find the radius of convergence for this one? Should we use the ratio or the root test? Root is a good option. Ratio is also a good option. It doesn't really matter. As long as you remember your special limits, this one won't be too terrible to do with the root test. But if you can't, and the good news is, as we all know in mathematics at this point, especially in this course, if you try the root test and it doesn't work, just erase it and try the ratio test. But we're going to do the root test this time. So by the root test, we got the limit as n approaches infinity of the absolute value of x to the n over n, all raised to the 1 over n. And that will be equal to the limit as n approaches positive infinity of the absolute value of x divided by the nth root of n to the 1 over n. And we know what the limit as n approaches infinity of the nth root of n is. That approaches 1. That's by the special limits. You don't necessarily need to mention that on exams and things like that, but that's just for our notes to remind us. That's by that special limit. And so the limit of this is equal to absolute value of x. And because we want this thing to be convergent, we need this absolute value of x. That's the limit from the root test. We need that less than 1. Which means that the ROC, the radius, is just 1. We didn't need to solve anything like we did over here. Oh, I forgot to do these ones. I'll finish them up on the, I'll take care of them during the break. And we'll go from there. But yeah, let's look back at this one. Sorry, just for clarity. When we were finding the radius of convergence for this guy here, or girl, or them, it became 4 times the absolute value of x. So we had to solve it. We needed to set it less than 1 and then divide by 4. So our radius of convergence was 1/4 here. So in the same fashion here, but we didn't actually need to do anything with this one. It was just going to be 1 anyways. Okay, so now we found the radius of convergence. And because it works for all of them based on the previous theorem, that's the radius of convergence for f, f prime, and the integral. Now, let's find f prime of x and the integral of f of x dx. So first and foremost, I'm going to rewrite f of x, which is the sum from n equals 1 to infinity of x to the n over n, which is going to equal x plus x squared over 2 plus x cubed over 3 plus dot, 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 dot. And it starts at n equals 1. So and for people who came in just a little bit late, don't worry, I'm coming right back to this. But this was that important little last note that I wanted to add on here, is that you can basically just take the derivative of the generic term, and that will be basically finding the derivative term by term. So with this one, f prime of x is equal to the sum from n equals, we're not sure yet. We're going to put a question mark here, to infinity of d dx of x to the n over n. And by the by the power rule, the derivative of x to the n is n times x to the n minus 1. And 1 over n is just a constant. Yes, it is something that varies, but for a generic fixed n value, that 1 over n is a constant. So it kind of just sticks around. So this would be equal to the sum from question mark to infinity of n x to the, let me just write this beneath it, actually, just to save on space. This will be equal to n x to the n divided by n minus 1, excuse me, divided by n. So it's going to be x to the n minus 1. Is that okay so far? Any questions on that? Now, I want to make sure that it lines up with when I take the derivative by term as it's written out. I want to make sure that it lines up. So from here, that's going to be 1 plus x squared plus x cubed plus dot, 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 on forever. Does that make sense? Looking at it term by term, the derivative of x is 1, the derivative of x squared over 2 is just x to the first power, x cubed divided by 3, derivative of that would be x squared, and so on and so forth. So what should n start with? Should it start with 1? Should it start with 2? 3, 0? What do you think? 1. So this time, the summation, the index, the lower bound of the index, it didn't change. So let's write a little note here. Since its first term is 1, index starts at n equals 1. So f prime of x is equal to the sum from n equals 1 to infinity of x to the n minus 1. Now we can re-index that if we want. We can make it start at 0, right? We could bring the index down by 1, which would mean that we need to counterbalance it in everything inside the general term, making it start at x n equals 2. Or sorry, start at n, excuse me. But this is fine enough. Unless I ask you specifically to change your index, you don't need to. So that's the derivative. Any questions on that? So you can take the derivative term by term. Let's recap that one more time because this is strange at first. So the previous theorem, the differentiation and integration of power series theorem, says that you can basically bring the derivative operation onto the inside of the summation, which is what we did. And then we weren't sure where it started, so we had to just verify it at first. 9 times out of 10, it will just increase the indices lower bound by 1, but this is an example where it doesn't. Happens. All right, that's f primes. Now let's find the integral. The integral of f of x dx is going to equal the summation of the integral of x to the n over n dx from n equals 0 to, or n equals 1 to infinity. And remember, n is just a constant. It's a fixed number for each n value. It doesn't vary at all, so it's not, you can treat it as a constant. And so this is really just 1 over n times x to the n. So by the power rule for integration, this will equal 1 over n times x to the n plus 1 over n plus 1. So this is going to equal, and remember, we integrated, and so we're finding a general antiderivative, so don't forget about your consistency, right? So capital C plus the sum from n equals 1 to infinity of 1 over n squared plus n times x to the n plus 1. Now let's verify that with term-by-term integration to verify that it does actually start with the same indice. So if I were to integrate x, I would get 1/2 x squared, right? Well, there's a constant c plus a 1/2 x squared plus a 1/6 x cubed plus a 1/12 x to the fourth plus dot 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 on forever. Do we see why that is? Okay, if we don't, please ask a question. If you don't, this is weird. We're finally getting back to calculus a little bit. We had to take that detour into real analysis, essentially. We just started real analysis. Now, does this line up with an n value of 1? If n is equal to 1, you get x squared, good. 1 squared plus 1 is 2, good. If I plug in n equals 2, I should get the next term in the sequence. That would be x cubed, good. Over 2 squared, which is 4, plus 2 is 6, good. I'm probably right. So my index doesn't change. And that's almost always the case. Integration, and this is something that you should know about, integration usually makes something more stable. Because the more derivatives you take, the more unstable it can get. Like you might have noticed that with derivatives, they start to get messier and messier and messier as time goes on, with product rules and quotient rules. But integration usually makes something go from something more complicated to something more simple. So, anyways, that is the integral of f(x) dx. Cool? Now that we have the two functions, now we can actually answer the question, because the question was asking to find the intervals of convergence for all three of these functions. Now, let's find IOCs. For f, well, first and foremost, we got x is less than 1. So that means that -1 is less than x is less than 1, which means the open interval of convergence is -1 to 1. Now we just need to test the endpoints. The radius of convergence never increases or decreases with integration or differentiation, but the interval of convergence may change. So we need to test the end bounds. At x equals -1, we would get the sum. So unfortunately, I don't have it in front of me. It's on your paper, so you can look back up. But f of x was x to the n over n. So plugging in -1 gives me the sum from -1 to the n over n from n equals 1 to infinity. Is that convergent or divergent? Convergent by what? By the alternating series test. And you can verify it, and we could if we really wanted to, and we probably should in an exam scenario. But honestly, at this point, since you've been tested on that, I am okay with you claiming that it's convergent by the alternating series test. You should verify it in your head, but you don't need to write out all the specific proof on these types of problems. If on the final exam there's a question that says, prove that this series, not a power series, but a series is convergent, then I need to see all of it. But if it's a power series question, it's asking to find the interval of convergence, you can just write convergent by alt series. And at x equals 1, we get this. We get n equals 1 to infinity of 1 to the n, which is just 1 over n, and that's divergent by p-test. So you can include -1, you cannot include 1. So the interval of convergence for f is bracket -1 to 1 parenthesis. Any questions? Next one, let's do the derivative for f prime. At x equals -1, we get the sum. F prime of x was this. So if I plug in -1 for x, I get the sum from n equals 1 to infinity of -1 to the n minus 1. Is that convergent or divergent? It's a quick one. It's divergent by the divergence test, right? The limit of your sequence inside your series, the limit of this sequence is non-existent. It does not equal 0, and therefore by the divergence test, it is divergent. So divergent by div test. And at x equals 1, we get the sum from n equals 1 to infinity of 1. And that is also divergent by the divergence test, because that's just going to be adding up 1 infinitely many times. So the interval of convergence for the derivative is -1 to 1, not including either. Derek, yes. Oh, you're just okay. Good. Last but not least, let's do the integral for the integral of f of x dx. And I know we're running out of space. I needed to be more careful with my upper space. I'll do that better next time. Well, that doesn't help you guys. All right. So at x equals -1, we get the summation from n equals 1 to infinity. Yes, there's a c out front, but c is just a constant, so I don't really need to worry about convergence of that. It's just going to be some number. So, but if I plug that into my antiderivative, I get -1 to the n minus 1, or to the n plus 1, excuse me, over n squared plus n, which is convergent by alt series. Which you can verify, we can do it in our heads. Ignoring the -1, every term is positive, 1 over n squared plus n, because n is ranging from 1 to infinity, 1 over n squared plus n is positive. Its limit will go to 0, and it is a decreasing thing. If you increase the indice by 1, you're going to get a bigger denominator, which results in a smaller fraction. So the larger you go, the further out you go, the smaller the number. So it decreases in size. So it is convergent by the alternating series test. And at x equals 1, we get the sum from n equals 1 to infinity of 1 over n squared plus n. And is that convergent? What do you think? I'm asking you guys, I don't know. I'm a fraud up here. I just been looking at notes this entire time, spouting off whatever it says. I got the real Philip Cook in my trunk right now. So is this convergent or divergent? Convergent by what? Direct comparison would work, or limit comparison with 1 over n squared. Convergent by limit comparison, limit comp with 1 over n squared. It's 1 over n squared. Whenever we see a rational series, we should always think about limit comparison or direct comparison. And this one, if you compare it with 1 over n squared, which is convergent by the p-test, you'll see this convergent. So the integral converges at both the left endpoint and the right endpoint. So -1 to 1. And so those are our answers. That's the interval of convergence for f, integral of f, sorry, derivative of f, and f itself. So I kind of want to bring something to your, do you notice anything? The derivative made it less stable. The derivative, we lost an endpoint. We went from bracket -1 to parenthesis -1. Whereas when we integrated, we gained a point. We gained an x value. That is the usual convention about integration and differentiation. Integration typically makes it more stable or keeps it the same. It's all right. So Does that always happen? Does it always end up being that what's it called? The integral gains one and the derivative loses one? No, it's not always guaranteed. Sometimes they all have the same radius of interval of convergence. Sometimes the derivative loses one and the integral is the exact same. Sometimes the integral gains one and the derivative stays the same, and vice versa, and all that jazz. So it is something where you have to test it every single time, except for the next case. Because these are my favorite ones. These are my favorite ones because, as you'll see. So given f of x is equal to the sum from k equals 0 to infinity of x to the k over k factorial, find the intervals of convergence for f, f prime, and the integral of f. So once again, if we want to find the intervals of convergence, we need to find out the radius of convergence. So first, ROC of f. Because the radius of convergence for f will be the radius of convergence for the derivative and the integral. What test should we use? Ratio, because it's involving a factorial. So by the ratio, we've got the limit as n approaches positive infinity, or k in this case. It doesn't really matter as long as you're consistent with your index. X to the k plus 1 over k plus 1 factorial all over x to the k over k factorial. And in the interest of space and for time, you're going to flip and multiply, but that's going to cause all the x to the k's to cancel except for that x to the first power. And that's going to, and k plus 1 factorial is really k plus 1 times k factorial. So this ends up being equal to the limit as k approaches positive infinity of absolute value of x divided by k plus 1. Any questions on that? Please ask it if you have one. I'm hopeful I can trust you guys with all the algebra that's happened here. There's a lot going on, but we're ready for it now. Calc 1, I was a little more hands-on with the algebra manipulations. With you guys, I'm a little less. So unless it's something we haven't seen before, then we take a little bit of time. So we got this. Now, x is going to be a variable, and it will vary over time, yes. But at the end of the day, we pick an x value, then we plug in the limit. So even if x is 10 billion, then we take the limit of 10 billion over k plus 1 as k goes to infinity, and that will go to 0. So this equals 0 for all x, which means that the limit of absolute value of x over k plus 1 is strictly less than 1 for all x. What would that mean about its radius of convergence? Everything. The radius of convergence is infinity. And so we don't need to do anything to find the intervals of convergence for f, f prime, and the integral, because they all have the same radius of convergence, right? So the interval of convergence for f is now everything. And that means because f prime has a radius convergence of infinity, its interval of convergence is everything. And because the integral of f of x also has a radius of convergence of infinity, that means its interval of convergence is everything as well. We don't need to do any testing. So kudos to us. But regardless, we should still find the derivative and the integral and everything just to see what happens. So now, so note, technically, we're done because all three have same. Oh, we should write this below the Sorry, I jumped the gun a little bit. This means that r is equal to infinity. So the radius convergence is infinity, and technically we're done because all three have the same radius convergence, which is equal to infinity, which automatically makes their IOCs equal to negative infinity to positive infinity, or R if you want to be a badass, right? If you want to be a math magician, as it were, you can just write capital R to mean all real numbers. But let's still go through the motions because there's something I want to see about this one, okay? But let's still find f prime of x and the integral of f of x dx. So f of x was equal to the sum from n equals 0 to infinity of x to the n over n factorial, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 on forever. It just so happens the two versions I pick. Oh no. Okay. So we take the derivative, right? F prime of x would be the sum from n equals 0 to n equals question mark to infinity. I'm not certain until I look at the term by term thing. That's just me. I want to be 100% certain. It's probably going to be n equals 1. Usually speaking, as a rule of thumb, is that if it has a constant term, like this one does, it has 1 as its constant term, chances are, if you differentiate it, the index will go up by 1. If it doesn't have a constant term, typically speaking, the index stays the same. So looking back at this previous example, this function didn't have a constant term. It just started with x to the first power, and its index stayed at n equals 1. If there is a constant term, 9 times out of 10, I'd say that the index will go up by 1 with differentiation. But let's be extra certain. So it would be ddx of x to the n over n factorial. But what that's going to be, and I'll write that right beneath it, that's going to be n times x to the n minus 1 over n factorial. But remember that n factorial is n times n minus 1 factorial. So the n's cancel. And so this will equal the sum from n equals question mark to infinity of x to the n minus 1 over n minus 1 factorial. Cool. Any questions so far? Now let's differentiate it each term individually to see what happens. So with this, let's use green. We get 0 plus 1 plus x cubed, or sorry, x squared over 2 factorial plus dot, 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 dot. So what should n start with? So really, we don't need to worry about the 0. It's gone. Our first term is 1. So I'm going to, in fact, just erase the 0. Where does the index start? Test it out in your brain. Would it be n equals 1? Would it be n equals 0? Because if it's 0, then it's x to the -1 over -1 factorial. And -1 factorial at this moment in your mathematical career does not exist. Later on, you might find some ways to mess with it. There's a thing called the gamma function and the beta function. And those things can actually make us find factorials for halves and things like that, and negative numbers, which is pretty cool, right? The gamma, if you want to look it up, the gamma function is pretty awesome. And so is the beta function. Fascinating stuff. But either way, so it can't be n equals 0. It's got to be n equals 1, because if I plug in 1, I get x to the 0, which is 1 by necessity in this case, over 0 factorial, which is 1 by necessity. So 1. So implies n equals 1. So we got this from n equals 1 to infinity of x to the n minus 1 over n minus 1 factorial. Now I want you to write a little bar here, and we're gonna take care of it in just a moment, okay? Any questions? Okay. Now we'll also try to find the integral. Not try, we will. There is no try. The integral of f of x dx would equal the integral of this, the sum of the integral from n equals 1 to infinity of x to the n over n factorial dx. And what I wrote in pink and orange up above, if you can do that in your head, you are the world is your oyster. Do it, please. You don't need to show it. It's just for our note-taking purposes. So when I integrate this, once again, the fact of the matter is n is a fixed number for each n value. So this is equal to x to the n plus 1 over n plus 1 times 1 over n factorial. But that's going to be equal to x to the n plus 1 over n plus 1 factorial. Do we all see that? Because n plus 1 is just 1 more than n. So n plus 1 times n factorial can be combined together to an n plus 1 factorial. So this is equal to capital C. Don't forget about your consistency. You integrated, which means you get a constant, plus the sum from n equals 1 to infinity of x to the n plus 1 over n plus 1 factorial. Oh, no, n equals 0. Excuse me, n equals 0. What am I doing? Please change those to n equals 0s. Okay. Now, here's where things get a little bit interesting. Unless there's any questions on this. So the first one with the derivative. What would happen if I reindex that to n equals 0? I'd be reducing the lower bound of the index. So what would happen to the sequence itself? Would it go up by 1 or would it go down by 1? Up, because it's a counterbalancing act, right? If you decrease the index, you increase it in the sequence. If you increase the index, you decrease it in the sequence. So what we're going to write here is reindex to n equals 0. And what we end up with is the sum from n equals 0 to infinity of x to the n over n factorial. But that's f. That's strange. You take its derivative and you get itself. Interesting. There are a few functions with that property, specifically two, but with the next one. So we can't like we could do that, but it wouldn't. We wanted to start with the same indice. It's already at n equals 0. So what we're going to do is we're going to do something that you will see more and more, especially as you move on in mathematics. Remember that c is a constant. It's any constant we can think of, right? So what we're going to rewrite this as c tilde plus the sum from n equals 0 to infinity of x to the n over n factorial, where c tilde is equal to c minus 1. So, well, let's do you see how that's going to work? If not, it's okay. Let me show. Let me explain. Let me write this a little more detail. So this is equal to c plus x squared over 2 factorial plus dot, 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 which we're going to equal to c plus minus 1 plus 1 plus x squared over 2 factorial plus dot, 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 dot. This is c tilde. It's a new constant, but it's the same thing. You can always do that with mathematics. You can really, if you have an integral and you get a constant, you can kind of rearrange the constant however you want. You'll see that a lot if you plan on taking Math 285. Not a lot, but you will see it happen every once in a while where like, I don't like that constant. I'm going to rewrite it. I'm going to rewrite it as something else. You see that a little bit. And that's just mathematics playing a little bit of God, right? We're close to deities. That is the perk of being a mathematician. What is it? What is it? In the Avengers, the Guardians of the Galaxy 2. What is the his father's name? Like Anton Ego. He is not a god. He's like a lowercase god, right? Lowercase god. That's what we are as mathematicians. So we're just better. That's the perk you get. The payoff, the downgrade is that you don't make money. All right. But it's worth it. So this is equal to c tilde plus the sum from n equals 0 to infinity of x to the n over n factorial. So, and by the way, the IOCs for all are negative infinity to positive infinity by the note above. So, what is the only non-zero function that has this unique characteristic where its derivative is the same as its original self and its integral is the same as its original self? E to the x. It's the only function that does that. E to the x. So e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. And what we learned in Math 126, way back, when we started talking about exponential functions, was that there was another way to write a limit, like write e as a limit. Do you guys remember what it was? But it's also equal to the limit as n approaches positive infinity of 1 plus x over n raised to the n. So isn't that bonkers? It can be written as a limit at infinity, or it can be written as an infinite series. Very few functions can do that, by the way. So there's another reason why I like e, the exponential number, the natural base, way more than pi. Everyone's always all up in arms and excited about Pi Day, March 14th. Yeah, big deal. Who cares about Pi Day? I want E Day, where we have eclairs instead of pie. Can't think of, I mean, what's a dessert that starts with E besides an eclair? If you can think of one, please let me know. Maybe we can eat eggplant parmesan, something like that. I don't know. But An egg pie, an egg custard tart. Hell yeah, hell yeah. It's delicious if you haven't had one before. But yeah, so marvel at the beauty of E. It's the only function that does this. It's amazing. All right. Any questions on this? Good. Can I move away from it? Okay. Now on to representation of of functions as power series. The whole reason why we did that last problem is to say, hey, we can write functions as power series, at least some of them. Which functions can we do that for? And not many, but a few. And you'd be surprised at actually how many we can do. So please remember from unit 3 that the geometric series, provided that your R value is strictly less than 1, the geometric series, converges to A. That's a typo. Sorry, 1 second. Let me add that to unit 4.3, typo A over 1 minus R. I'll know what I mean. Famous last words. Okay. So provided that your R value is strictly less than 1, A times R to the K for K to 0 to infinity converges to A over 1 over R, or A over 1 minus R. And if we decided to make R vary instead, if we look at just a generic geometric series, and instead of writing it as R, we can write it as X and just make X vary between -1 and 1. We would get a pretty cool function. Y equals 1 over X is equal to the sum from K equals 0 to infinity of X to the K. It's a geometric power series centered at X equals 0 because it's not X, it's X minus 0 to the K, with an interval of convergence of -1 to 1. As you can imagine, it doesn't include the endpoints because if you plug in -1, you're going to get -1 to the K, which is divergent by the divergence test, and same thing with 1. You get 1 to the K, which is 1, adding up infinitely many times. Now, that is great. It's cool. Super dope, as the kids say, right? But it's better to look at it in a different light. We can make X whatever we want. And by function composition, that means that we can actually better think about it as 1 over 1 minus a blue box is equal to the sum from K equals 0 to infinity of blue box to the K. So as long as we can get a function to look as 1 over 1 minus a block, we can write it that way. Does that make sense? That is key. As we go on to math, to unit 1.4.4, which will be on Taylor and Maclaurin series, not polynomials, but series, we will learn a few more special functions that we can write as series, as power series. They will be provided on the exam. You do not, on the final exam, you do not need to have them memorized. Those things are things that when you become a math major, sure, you can have them memorized, but for now, I don't really need you to know it too well. How to manipulate it, how to play with it, sure, but not necessarily how to memorize it. So find a power series for the function 1 over x. Find its center and its interval of convergence. So at the end of the day, it is 1 over something. We want to get it to look like this. We want 1 over x to look like 1 over 1 minus a box. And how will we do that? How do you think you could do that? is a very common tool that mathematicians use all the time. One of them is cleverly multiplying by 1. We do that all the time to find common denominators. But there's another thing that we've learned. Not cleverly multiplying by 1, but cleverly adding 0. So 1 over x, you could rewrite that as, well, I need to have a 1. I need to. In order for this to work out, I need to have a 1. So why not just add 1 and then subtract 1 plus x? Why not do that? Well, that's good, but that's not all the way. Because what I need to do is I need to get this in the form of 1 minus x, like 1 minus a box. So I'm going to rewrite this as 1 over how do I want to mess with this? There's a number of ways to mess around with it, but I want my x to stay positive. So what if I were to write this as -1 plus x plus 1? I'll leave the -1 on the outside and then group together the x plus the 1. Now that doesn't look perfect because I have a positive 1 and a minus, right? So what's to stop me from multiplying by -1 over -1? I'll do that. I'll multiply by -1 over -1, and I end up with 1 over 1 minus parentheses x plus 1 and a -1 up top. Now this is my box. And if this one seems really, really convoluted and difficult, you're not alone. It took me like when I was looking at this and I was thinking about it, because I hadn't looked at this in a while. I was like, how do I do this? Okay. It's one of the ones that's so simple in its performance. Like it looks really, really simple, and those tend to be the hardest problems in my experience. If it looks simple, it's probably not. It's a good methodology to imply with mathematics. If it looks simple, it's probably really, really annoying. And this one was. So we can rewrite this as -1 times the sum of x plus 1 to the k, from k equals 0 to infinity, or that is to say, 1 over x equals the sum from k equals 0 to infinity of negative parentheses x plus 1 to the k. So where is it center? -1, because it needs to be x minus x sub 0. So this is x minus -1, which means that its center is x equals -1. And as it is just a different version of x to the k, it's a geometric series. So the absolute value of x plus 1 needs to be strictly less than 1. So for IOC, we need the absolute value of x plus 1 to be less than 1, which gives me -1 is less than x plus 1 is less than 1, which gives me x is sandwiched between -2 and 0. Then At x equals -2, it's divergent, and at x equals 0, it's also divergent. Take a second to confirm that for yourself. Let's talk through it one more time after people have written it down so we understand what's going on. So that is a geometric series. That being this thing right here. That's a geometric series because this is just a box to the k value. So we have, just like with the ratio and the root test, which we could have done to find the radius of convergence for this thing to be 1. We could have done that, and that would have worked out, and you would still get 1 at the end of the day. Or you can realize that the geometric series also have their own radius of convergence test. In particular, it is that the inside, the r value, which in this case is x plus 1, where x will vary, that needs to be strictly less than 1. That gives me this compound inequality. I'll subtract 1 from everything to get -2 to 0. So the open interval of convergence is -2 to 0. And we test the endpoints. At -2, if I plug in -2 into this, I'm going to get -1 to the k, which is divergent by the divergence test. And if I plug in 0, I'm going to get 1 to the k, which is just equal to 1, which is divergent by the divergence test. So the IOC is -2 to 0, parenthesis. And that is the series. Those are our 3 little notes. Any questions on that? That one, honestly, in my experience, is the hardest one of the bunch. The rest ones are cake in comparison, in my opinion. Still difficult, of course. This is calculus 2. This isn't algebra. But at the same time, that one, because it's just a 1 over x, it's really hard to manipulate it to be exactly what you need it to be. But it's a really good practice of algebra skills. Mess around with it until something sticks. Okay? Let's take our break. Let's come back at 10:05 or 1:05 or 11:05, and we'll come back. People watching the recording, go stretch your legs or something. So we're back, and this time we're going to be talking about how to find a power series representation of g of x is equal to 3 over 2x plus minus 1. So first and foremost, it's not in the perfect format because it's not 1 minus something. But there's an easy fix for that. So g of x is equal to 3 over 2x minus 1. It already has a constant of 1. That's good news. So what if I were to just factor out a -1? And then maybe this will make it look a little bit better. This is my blue box. That's my blue box. So the power series representation would be the sum, or will be -3 times the sum from k equals 0 to infinity, or n, or m, or whatever you want it to be, of parentheses 2x to the k. Which I'm just going to rewrite now as the sum from k equals 0 to infinity of -3 times 2 to the k, x to the k. Any questions on that? So we can do this because we're just imagining 2x as our box. And 1 over 1 minus box is equal to the sum from k equals 0 to infinity of box to the k. And then we just distribute the k throughout because it's multiplication here, and we get this. So where's that centered? I think I heard someone say it. 0, because it's just x, which is the same thing as x minus 0. Allergies are upon us. I don't know if anybody else is dying, but I'm dying. Ugh, took a Benadryl this morning because it was so bad, and now I'm feeling a little bit crazy. Uh, but anyways, we also need to find its interval of convergence. So we can still use the root test or the ratio test or whatever. So by root. However, there's a faster way is to leave it in this format right here. If you leave it like this, then you can use the geometric series test to determine convergence. But I don't expect us to be that clever on an exam, so let's just do it the normal way by the root test. Because you got a 2 to the k and an x to the k, that'll cancel out with the 1 over k really nicely. We got the limit as k goes to positive infinity of the absolute value of -3 times 2 to the k times x to the k, all raised to the 1 over k, which is going to equal 2 absolute value of x. I guess I should be a little more careful. I should say 3 to the 1 over k times 2 times the absolute value of x. Oh, limit. Dope. Sorry. Ah. But if you remember from our special limits, not only does n to the 1 over n go to, or k to the 1 over k go to 1, but any non-zero number raised to the 1 over k will also go to 1. So this will go to 1 by the special limit. So we end up with 2 absolute value of x, and we need that less than 1 to be convergent. In order for the root test to show convergence, we need it to be strictly less than 1. So that means that x is less than 1/2. Absolute value of x is less than 1/2. So the radius of convergence is 1/2, but we want the interval of convergence. So we need to solve for the open interval, test the endpoints, and see what happens. -1/2 is less than x, less than 1/2. And then at x equals -1/2, plugging that in, you're going to get, if you plug in -1/2, just visualize this in your head. If I plug in -1/2 here, it's going to be -1/2 to the k, which is really -1 to the k over 2 to the k. The 2 to the k's cancel. I'll have -3 times -1 to the k, which is divergent. And at x equals 1/2, it will also be divergent, but for a different reason. It'll be -3. We'll be adding up infinitely many -3s, which never converges by the divergence test. So the IOC is equal to -1/2 parenthesis to +1/2 parenthesis. And the series is -3 times 2 to the k times x to the k from k equals 0 to infinity. Oh, I didn't get those ones done. Okay, I will make sure next time I'll send out an email later today with the answers to those two problems from the previous set. Find their intervals of convergence, okay? In case you didn't do it yet. Any questions? Okay. So, another one. Find the power series representation of 1 over 1 minus x, but with center at -3. Okay. How would I do that? So y is equal to 1 over 1 minus x, but I want it to be centered at -3. So I want my box. So Keep in mind your objective. We want, don't write this down, but we want 1 over 1 minus x plus 3 here, right? Because if it's centered at -3, that's x minus -3. So what should I do? Cleverly adding 0 is always a good choice in mathematics. That's one of your bread and butter skills. That's one of your like probably not your hammer, right? If you're looking at your toolkit, your mathematical toolkit, not a hammer, maybe a measuring tape. You should always have a measuring tape in case you don't. Always have a measuring tape and a level. Level is very, very important. Anyways, so we're gonna get 1 over 1 minus, and then I'm gonna do it on the inside of the parentheses. I'm gonna do that to just x and then see what happens because, and I'll show you why in just a moment. I'm gonna write it while you're writing that down. Okay, so x plus 3 minus 3. And the reason why I've done this is that, I mean, it's not the end of the world, it's not the biggest deal, but if you were to do it like this, adding 3 and then minusing 3, remember you want it as 1 minus a box. So you actually want to pair it with the -3 to make it a +3 at the end of the day. So you might make a small error when you first start off with this red version, because you'll be like, okay, well, then that's going to be, let's just factor out the -1 here. But then it becomes this, which is not centered at -3, it's centered at +3. So, I mean, not the end of the world, but either way. I will make sure to distribute the minus sign to this. And what I end up with is 1 over 4 minus parentheses x plus 3. Now, John Doe student says, I've done it because I've written it as, oh, wait a minute, it's not 1. In order for it to be a geometric series, it needs to be centered at 1. Or it needs to be 1 over 1 minus a box. So what do I do? What do I do? What would you do? Multiply by 4 over 4. More specifically, factor out a 4. If you factor out a 4 from that, then the 4 becomes a 1. But because I factored out a 4, then what that does is that makes it that I have to divide x plus 3 by 4 to kind of counterbalance the fact that I factored out a 4 from something that didn't have a 4. So in parentheses, it is x plus 3 divided by 4. So what this equals, that is my box. So it's going to be 1/4 times the series from k equals 0 to infinity of x plus 3 over 4 to the k. Any questions so far? Okay. So working around with it, remember the x plus 3, you can't distribute the k throughout that because it's a sum, not a product of things. But I can distribute the k through the division. So this is equal to 1, it's equal to the series from k equals 0 to infinity of 1/4 times x plus 3 to the k over 4 to the k. And just rewriting that just a little bit nicer, that's the series from k equals 0 to infinity because it has the 1/4 I combine that with the 4 to the k, and I get 1 over 4 to the k plus 1 times x plus 3 to the k. Its center, well, we already know where the center is. It was required. We wanted it to be at -3. So, any questions so far? I need to find its radius of convergence and its interval of convergence. Now, this time, I'm going to look at this. I'm going to kind of go like this. Let's go like this. By geoseries, we need absolute value of x plus 3 over 4 to be strictly less than 1. Does that make sense? You can also use the ratio test or the root test. It will work out just as fine. But I'm cramped for space at this moment, so I'm going to skip that and just use the geometric series test. That means that x plus 3 absolute value needs to be less than 4. So now I want you to find the interval of convergence using that information. Does anybody have any questions before you guys work on it by yourselves? I want you to find the interval. And so I'll slowly fill in details. People watching the recording, you should do it yourself too. I have the answer up here. If you're still working on it, continue to do so. But I'm going to slowly fill in, like, kind of help you out through the process when we're talking. So we know that x plus 3 has to be strictly less than 4 because we multiplied by 4 in that absolute value, and we're all there. That sets up the compound inequality. And then we subtract 3 from all 3 pieces of the compound inequality. We get -7 is less than x is less than 1. That is the open interval of convergence, but we don't know about the endpoints. 9 times out of 10, maybe even 99,999 times out of 100,000, it won't include the endpoints when it comes to geometric series. It's very, very uncommon. But regardless, still need to test it. At x equals -7, x plus 3 will become -4. It'll cancel out the 4s, and you've got -1 to the k, which is or -1/4 times 1 -1, or 1 over 4 times -1 to the k, divergent. X equals 1. You get 4 to the k. They cancel out. You get 1/4 added up infinitely many times. It's also divergent. So the interval of convergence is -7 to 1. Any questions on that? Okay. Next one. Find a power series representation of y equals x over 4 plus x squared and find its interval of convergence. Okay. So I'm going to help you get started, and then I want you to finish it off. So first and foremost, if I rewrite y equals x over 4 plus x squared, that x is causing a problem in the numerator. So, because I don't know how to deal with an x in the numerator, so let's factor that out front for a second. Now, 1 over 4 plus x squared, we can work with that. But the problem is, once again, it does not fit into our criteria. So what should you do to get it to fit into the format of 1 minus a box? Trig sub would be a great idea because it looks exactly like a trig sub, but we're trying to get it to just be 1 over 1 minus a blank. It's a 1 plus right now, or it's a 4 plus. So we have two obstacles to overcome, the 4 and the plus.
X over X.
Well, it's a good idea. It's very, very similar to what we need to do. But the X over X won't actually solve anything for us because that's just going to increase the power to an X cubed over an X, and that's not going to get us much. We did it just up above. So let's first tackle the first obstacle, the 4. How do we deal with that? Isaac. Factor out a 4. So this becomes X times 1 over 4 times parentheses 1 plus X squared over 4. Now we have to deal with the fact that it's adding. How do I make it a subtraction? You've done it plenty in your mathematical career. Isn't adding X the same thing as subtracting negative X? Aha. So we rewrite this as X over 4 times 1 over 1 minus negative X squared over 4. Right? You can double negate. These whole problems are meant to show you the little tools that you need to work with in order to mess around with power series to your liking. So this is equal to, therefore, X over 4 times the power series from k equals 0 to infinity of negative X squared over 4 to the k. This is our blue box. Now let's go ahead and mess around with that, get it to be the right format. That will be the series from k equals 0 to infinity of negative 1 to the k times x to the 2k plus 1 over 4 to the k plus 1. Now, I am being a little bit of a cheater here because I'm multiplying an infinite sum by x. And I'm claiming that we can bring the x on the inside. And as I talked about at the very beginning, that's a very rare quality with infinity. Infinity is a weird concept. We've seen this over and over again with the Gabriel's horn situation. The fact that adding up an infinite number of rational numbers ends up being irrational. The sum of 1 over n squared converges to pi squared over 6, which is very, very strange. So why can I do that? As long as I am within the radius of convergence, that is possible. It's not always possible, but as long as I am within the radius of convergence, I can bring the x onto the inside. You have to be careful with that type of thing. You don't need to worry about it too much until you become a math major. But if you plan on taking upper division like real analysis and stuff, they'll make you verify that before you can claim any of those things with infinity. But I digress. That is the formula. Any questions on that? Okay. So that is the series, but it also wants us to find the interval of convergence. Now, I'm going to do the ratio test because trying to take the nth root or the kth root of 2k plus 1 is not impossible to do. It's not too terrible, but I'm going to just stick with the ratio test. So by ratio, you get the limit as k approaches positive infinity of the absolute value of -1 to the k plus 1 times x to the 2k plus 3 all over 4 to the k plus 2 all over the big division bar, -1 to the k, x to the 2k plus 1 over 4k plus 1, 4 to the k plus 1. Any questions on that?
Why is it two X up to K plus three?
Why is it indeed? Does anybody have an answer for that? Because we're going to replace the k with a k plus 1. Excellent question. So for this, the reason is it's 2 times k plus 1 plus 1. It's 2k plus 2 plus 1, which is 2k plus 3. Is that okay? Excellent question. So remember, we're replacing the, like, when we do a sub k plus 1, we're replacing every instance of k, just the k, in the sequence with a k plus 1. So that 2k plus 1 becomes 2 times k plus 1 plus 1, which is where we get 2k plus 3. Now, saving on a little bit of algebra, hopefully you can see this in your brain. The -1s, because they're inside an absolute value, they don't matter. They go away. X to the 2k plus 1 and x to the 2k plus 3, they cancel, leaving us with just an x squared, absolute valued. 4k plus 1 over 4k, 4k plus 2 over 4k plus 1. The k's cancel, the 1's cancel. We're left with just a 1/4. So this becomes the limit as k approaches positive infinity of the absolute value of x quantity squared over 4. And in fact, we don't even need a limit anymore. All the k's ended up canceling. So it just equals absolute value of x squared, which is a little redundant, right? X squared makes it always positive, so you don't really need them there, but still. And that gives me absolute value of x squared over 4, and we need that less than 1. That gives me absolute value of x squared needs to be less than 4. And yes, I do need to put the plus or minus, but it's already sandwiched between -4 and 4. So putting a plus or the minus would be kind of redundant. Does everyone understand that? It's okay if you don't. Once again, so like technically to solve this, I would need to take the square root of both sides. And when you take the square root, you do the plus or the minus. But because it's an absolute value that's sandwiched with a less than, it becomes a compounded equality. So putting the plus to the minus just gives me two versions of the same compounded equality. That's all it does. So what this ends up giving me is absolute value of x needs to be less than 2. And so -2 is less than x is less than 2. And then at x equals -2, if I plug in -2, that's really just -2 to the 2k plus, times -2 to the first power. The negatives will be fine. There'll be a thingy. It'll be fine. But then you got x squared, 2 to the 2k, which is really 4 to the k. It cancels out the things. We get a constant with a -1 to a power. It'll be divergent. And at x equals 2, it'll also be divergent. So this is the power series. Its center is 0, and its IOC is -2 to 2, parenthesis, without including the end points. Any questions? Okay? So this is how we can manipulate them. This is how we can manipulate things to see how we fit. This example is to show you that you can factor out some finite x's at sometimes. You can rewrite things as a minus and negative. You can double negate, and you can factor out constants to make sure you get that 1 minus a box. And it's okay for you to have other powers. It could have been x cubed, and that would have been fine too. It could have been x to the 19th, and that would have been fine too. We just like what would end up happening is we get an x to the 19th instead of an x squared absolute valued, and then we'd have to take the 19th root. But who wants to take a 19th root of 4? That doesn't sound fun. It's probably going to be about 1. But either way. All right. Next. Back to that theorem. That theorem from the beginning of the hour. The differentiation and integration of power series. We know how to represent functions that form 1 minus a box. We can differentiate that or integrate that by regular rules, right? By the chain rule or the quotient rule or the whatever rules we want to really work with. And because of that theorem, 4.2.2, and we know that it's a series, we can integrate or differentiate it term by term. So, as an example, find a power series for the function 1 over 1 minus x to the quantity squared. Key observation. Do you notice any connect? So the problem is we cannot write this as a power series. If it was 1 over 1 minus x squared, this is our box, and we could write this as the sum of x squared to the k, and that would be fine. But it's not 1 minus x squared. It's the quantity 1 minus x squared. Now, there is a way to do it without doing what I'm about to say, which is that you can rewrite this as 1 minus x times 1 over 1 minus x. And so you can write it as the product of two power series. And then there's a theorem. If you look at any textbook on power series, I don't go over it because it's something that's really for upper division mathematics. You can, as long as you work on the smallest interval of convergence between the two series, you can multiply series together. But then their coefficients become awful. So I would recommend not doing that and instead realizing that if y is equal to 1 over 1 minus x, which is really 1 minus x to the negative 1, that implies that y prime is negative 1 times 1 minus x to the negative 2 times negative 1, which is 1 over 1 minus x quantity squared. So 1 over 1 minus x squared is the derivative of 1 over 1 minus x. And we know what the power series representation of 1 minus 1 over x is. This is equal to the series from k equals 0 to infinity of x to the k. So that implies that this is the derivative of the power series x to the k from k equals 0 to infinity. Does that make sense? So be on the lookout for these types of things. If you're being asked to find a power series in this class, you need to be able to relate it some way back to probably a geometric series or some of the series that we'll find out soon enough. We're not there yet, but we will get there. All right. So by theorem 4.2.2, or let's call, we shouldn't call this y. We should have called this f of x. Because y was already taken. Apologies. Rewrite it as f of x. So f prime of x is 1 over 1 minus x squared, which is equal to y. I don't know, the same thing. I have the same question about my my watch. Sometimes it just takes just gets in the way. So by theorem 4.2 by 2, y equals 1 over 1 minus x squared is equal to the series from k equals question mark to infinity of d dx of x to the k, which is equal to the series from k equals question mark to infinity of k x to the k minus 1. Now, I'm not like the reason why I put the question mark is because I'm not certain yet. Not certain whether it should go up by 1. It probably will because it has a constant term. And what I said before is that 9 times out of 10, if it has a constant term, when you differentiate it, the index should go up by 1. But let's verify that before plugging it in. The first function, x to the k, would be 1 plus x squared plus dot, 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 dot. The derivative of that would be 1 plus 2x plus 3x squared plus dot, 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 dot. So that's what the derivative should be. So what should k start with? If it was 0, it would actually work out because k times 0 would be 0 times 0 to the 0, which by necessity would be 1 here. And so that would go away, but it's better to just start it at 1. So we'll make it go to k equals 1. And so that's its power series. And its center is at x equals 0. Sure, we'll do a parabola. That's fun. No. Can I not get it off? Is this really necessary, Phil? Yes. Okay. So its center is at x equals 0. And then it has the same radius of convergence as 1 over x. Y has same ROC as 1 over 1 minus x, which is 1. Because 1 over 1 minus x is x to the k, and that has a radius of convergence of 1, as we saw earlier. So we've got absolute value of x needs to be less than 1, which gives me -1 is less than x is less than 1. And then at x equals -1, it'll be divergent. And at x equals +1, it will be divergent as well. So the IOC is -1 to 1. Now, as I said before, though, once again, if you differentiate, it usually makes it more unstable. And if you integrate it, it usually makes it more stable. So since the original function has an interval of convergence of -1 to 1, as we already saw in the first page of this thing, this one should be either the same size or decreased. It can't decrease anymore. It can't get rid of any endpoints because there are no endpoints to get rid of. So it should stay -1 to 1. So you could probably just claim it's -1 to 1 without any proof, and that would be fine. But that's the reason why. This is a formal proof of it, but you can also just claim it's -1 to 1 because when you differentiate, it makes it more unstable. Cool? So cool. Okay. '45. This is our last problem. This one is a fun problem to do at some point, if you're curious. We won't be able to finish the next one, but we will get to it for right now. So find a power series representation of P of X equals natural log of X plus 1. Hmm. Hmm. Mm-hmm. The derivative of P of X, so key observation number 1, P prime of X is equal to 1 over X plus 1 times 1, which I can rewrite as 1 over 1 plus X, which I can then rewrite as 1 over 1 minus negative X, which is equal to the series. Okay, no. And that's what key observation number 2 is. So underneath this, underneath key observation number 1, if I integrate, so integrating 1 over 1 minus negative X's power series will give me a power series for P of X. The derivative of my function is a power series, like it is a function that I can write a power series of. So I have to undo the power series of 1 over 1 minus X, 1 minus negative X, by undoing it, what I mean is integrate it to get a power series for natural log of 1 over X. Key observation number 2 is that 1 over 1 minus negative X is equal to the series of negative X to the K, which is equal to, from K equals 0 to infinity, which is the series from K equals 0 to infinity of negative 1 to the K, X to the K. We'll utilize this when we come back to find the power series for natural log. We'll utilize that in just a moment, but that'll be something to have fun with on the weekend. So what's cool about this, in my opinion, is once we found a power series representation of natural log of X plus 1, we can now figure out a series notation for any irrational natural log. We can now, like, once we find the series, let's just say for the sake of an argument, natural log of X plus 1 is equal to, the answer, by the way, will be negative 1 to the n over n plus 1 times x to the n plus 1. What we can now do is, provided we're on the interval of convergence, we can now find out what natural log of 2 is equal to as a series, which, I mean, big deal, big whoop, right? It's not that big of a deal, but I think it's a big deal. I think it's pretty cool. We can now find a way to represent an irrational number as a sum, an infinite sum of rational numbers. We can be pretty dope, as the kids say. So anyways, that is the answer if you want to try it this weekend. Find the power series representation for this with our 1 minute left. What do you think we should do? Factoring it would be a good idea. And this factors to 2x plus 1. Wait, no, 2x minus 1 times x plus 2. And man, when I see a rational function, think about one thing in particular. How could I decompose it? You guys ready for some partial fraction decomposition? Hell yeah, you are. Do this over the weekend. It'll be a fun time. I don't remember what the answer is off the top of my head, but I'll make sure it's there available for us after that. Anyways, that'll do it for today and for this week. We'll come back next week with a quiz on Tuesday. What is the quiz on Tuesday for? On just 4.1 and 4.2. So we won't have anything on 4.3. And then we'll go ahead and start up with Taylor series and Maclaurin series. If you have any questions, please feel free to ask. Otherwise, you guys have a great rest of your day. a great weekend. Avoid doom scrolling and avoid, more specifically, be in charge of your media consumption. Be in charge of it. It's much better than letting an algorithm decide it for you guys. Have a great weekend.